Good morning, dear children. Today we are going to study a new lesson, lesson number 5, that is periodic table. Now let us see the content of the lesson. First we are going to see introduction, then we are going to study classification of elements. In classification of elements, we are going to study Dobberinier law of triads, Newland's law of octaves. Then we are going to study Mendeleev's contribution and modern periodic law. Now before we start the lesson, let us take a quick recap of what we have learned in the previous chapter, that is atomic structure. Now what is an atom? Atom is the smallest particle of an element. It contains equal number of protons and electrons. It also contains neutron. Atom is electrically neutral. Now what are elements? Elements are the basic unit of matter. Elements are further classified into metals, non-metals and metalloids. Metals lose electron. It can lose 1, 2 or 3 electrons and it develops a positive charge. Number of protons exceeds number of electrons and metals form cation. Non-metal gains electron, it develops a negative charge and form anion. Now atomic number. Atomic number is given by the alphabet capital Z. Atomic number is equal to number of protons and number of protons is equal to number of electrons. Now what is atomic mass number? Atomic mass number is number of protons plus number of neutrons. Now neutrons and protons together are called as nucleons. And atomic mass number is given by capital A. Electronic configuration. What is electronic configuration? Electronic configuration is distribution of electrons in shell. Now let us consider example of two elements, aluminium and chlorine. Aluminium atomic number 13, so electron distribution is 2, 8, 3 and chlorine is 2, 8, 7. Now based on the electronic configuration, we have studied valency. What is valency? Valency is combining capacity of an element. The elements, they always try to become stable and try to achieve the configuration of nearest noble gas. So in case of aluminium, it would lose 3 electrons and so valency of aluminium is 3. Let us take a look at chlorine 2, 8, 7. It requires 1 electron to complete its octet. So it's more easier for chlorine to accept 1 electron rather than losing 7 electrons. Its valency is 1. We are going to study first 20 elements. We are going to see basis of classification of elements. Classification of elements was given by the early chemists. Now how the classification of elements was done? It was done on the basis of properties, valencies, metallic and non-metallic nature of elements. Now let us see the classification of elements one by one. Now Dobberinier law of triads. Chemical analogous elements were arranged in increasing order of atomic weights, form well marked of group of 3 called triads, in which the atomic weight of the middle element was found to be the average or arithmetic mean of the other 2 elements. Now let us consider this example of lithium, sodium and potassium. Now if we add the atomic weight of lithium and potassium, it will give the arithmetic mean of sodium. Now 39 plus 7, it becomes 46 and if we divide it by 2, it will give us 20. So we have added the atomic weight of lithium and potassium, and which was found to be the arithmetic mean of sodium. Now this method was disordered of elements and it was not holding true for all the elements. Property of elements grouped into triad were found not to be similar. So these elements, they did not have similar properties. So what Dauberignier has done, he has tried grouping of elements in 3 and he called them as triads. He classified elements on the basis of atomic weight. He found that it was not applicable to all the elements, and that's why his theory failed. So we know his contribution. Okay, now let us see.
We all know that matter can exist in the form of elements, compounds, and mixtures. When elements were discovered, a proper classification was required for their easier and better understanding. Many scientists adopted different ways to classify them. They tried to find out some pattern or regularity in the properties of elements.
There are thousands of medicine in a medical shop, but the chemist will find any medicine in matter of seconds, right? So that is the beauty of proper arrangement. Talking about elements, there are 118 known elements, but not every element is absolutely unique in all aspects. There are many similarities between several elements too. Hence, scientists try to arrange the elements into groups based on similar properties. And the arrangement is meant to relate different elements so that we can remember the properties of all the elements by remembering the properties of fewer elements only. A brilliant idea. But that task wasn't as simple as it sounds. You know, in the year 1817, Johann Wolfgang Dauberignier, a German chemist, tried to arrange the elements in group of threes and call those triads. When the elements in a triad are written in the order of atomic masses, then the atomic mass of the middle element seems to be roughly average of the other two elements' atomic masses. But he only managed to find 3 such triads based on similarities in properties. The first triad consisted of elements lithium, sodium, and potassium. If you see, the atomic mass of lithium is 7 and that of potassium is 39. Now, the arithmetic mean of the atomic masses of these two, that is lithium and potassium, is 39 plus 7 divided by 2, which is equal to 46 divided by 2, and this is equal to 23. And sodium, which is the middle element in this triad, has atomic mass which is equal to 23. And as we saw, it is the arithmetic mean of the atomic masses of lithium and potassium. The second triad consists of calcium, strontium, and barium. Here, the atomic mass of calcium is 40 and that of barium is 137. Now, the arithmetic mean of the atomic masses of these two elements is 40 plus 137 divided by 2, which is equal to 88.5. Also, Strontium, which is the middle element in this triad, has atomic mass equal to 88, and as we saw, it is approximately equal to the arithmetic mean of the atomic masses of calcium and barium, which is 88.5. And the third triad consisted of chlorine, bromine and iodine. Now, chlorine has the atomic mass of 35.5, bromine is equal to 80, and for iodine it is equal to 88.5. If you see, the mean of atomic masses of chlorine and iodine is equal to 35.5 plus 127 divided by 2, which is equal to 81.5. And this is approximately equal to the atomic mass of the middle element, which is bromine, and it is equal to 80. So we see Dobereiner only managed to find 3 such triads based on similarities in properties. Thus, there were limitations to this. And what are the limitations? First of all known elements could not be arranged in form of triads. Secondly, the law failed for very low and very high masses. Lastly, as the techniques improved for measuring atomic masses accurately, the law could not remain strictly valid. So to sum up what we learned today, Dobereiner's law of triads states that when elements are placed in order of ascending order of atomic masses, groups of 3 elements having similar properties are obtained. And the atomic mass of the middle element is nearly the same as the average of the atomic masses of the other 2 elements. That's all for now. Bye-bye.
Now let us see Newland's law of octave. Now elements, when arranged in increasing order of their atomic weights, show resemblance in their physical and chemical properties between the 8th and 1st element. Now let us see this example. Here this is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, sodium, magnesium, aluminium, silicon, phosphorus, sulfur and chlorine. Now if we see from here, from lithium, sodium is the 8th element, and from fluorine, chlorine is the 8th element. So lithium and sodium show similarity in their properties, while fluorine and chlorine show similarity in their property. Now Newland arranged elements in increasing order of their atomic weight. He had compared to the octave of music, what we called it as sa, re, ga, ma, pa, dha, ni, sa, where he found that the 8th element had properties similar to that of the 1st element. Just now we have seen that lithium and sodium are having similar properties, while chlorine and fluorine also have similar properties. During that time, there were no noble gases. Later, noble gases came into existence, and therefore his theory failed. So this method showed odd grouping and failed to leave spaces for undiscovered elements. So he did not leave any space for undiscovered elements. Method of classification show meaning with light metals, like he has taken lithium and sodium, but he failed to explain it with the help of heavy metals or beyond it.
Newland's octaves. Newland, a British chemist, arranged all the known 56 elements in increasing order of their atomic masses and found that every 8th element had properties similar to that of the first, as in case of the octaves of music. Hence, this classification was known as Newland's octaves. Newland's law states that when the elements are arranged in an increasing order of their atomic masses, the properties of the eighth element are similar to the first. Some features of Newland's table. 1. Newland's law of octaves was applicable only up to calcium out of total 56 elements known at that time. 2. After calcium, every eighth element did not possess properties similar to that of the first. 3. Newland's assumed that only 56 elements existed, but later several elements were discovered. 4. To fit the existing elements, Newland's placed two elements in the same position which differed in their properties. 5. This periodic table did not include noble or inert gases because they were not discovered at that time.
Now let us study about Mendeleev's periodic law. Mendeleev was first scientist who had tried classifying the elements and thinking about the concept called periodic table. Mendeleev was the brain behind the periodic table, right? But he had classified all the elements on the basis of atomic weight. There were few defects in his periodic table. Now let us first see the contribution of Mendeleev. Elements were arranged in increasing order of atomic weight. Horizontal rows were called as period and vertical columns were called as groups. Elements are similar with respect to their chemical properties. They are grouped together and have atomic weight of nearly same. So they have same chemical properties and their atomic weight was also same. Elements in the same group had same valency and they also had similar chemical properties. Based on the periodicity of properties, a number of gaps were left for undiscovered elements. So he has left the gap for the undiscovered elements. The properties of undiscovered elements left in the vacant gap was predicted. So he had certain prediction about the undiscovered elements and the gaps which were left. Incorrect atomic weight of some of the arranged elements were corrected with the knowledge of atomic weight of adjacent elements. So few of the elements which had incorrect atomic weight were corrected based on the knowledge of the atomic weight of their adjacent elements. Now let us see about the defects of Mendeleev's periodic table. Position of isotope was there. There was discrepancy between cobalt and nickel, right? Cobalt was placed before nickel. He could not prove that. Remember, Mendeleev was the first to bring concept of periods and groups. Now, anomalous pairs of elements, certain pairs of elements having higher atomic weight have been given position before the elements having lower atomic weight. So higher were placed before lower. Position of rare earth and actinide could be justified only if arranged according to their atomic number. So he could justify the position only when the elements were arranged according to their atomic numbers. Position of isotope. Isotope had to be placed in same position according to the atomic number. So these were the defects of Mendeleev periodic table. This is important from the point of view of your exam. You should know his contribution as well as the defects which were found in his periodic table.
Mendeleev based his work on the research by Newlands and took it further. He felt that effective grouping of elements and prediction of properties could be based on two parameters: atomic weight and chemical reactivity. Mendeleev's periodic law states that the physical and chemical properties of all elements are a periodic function of their atomic masses. Let's look at the features of Mendeleev's periodic table. The table had 8 vertical columns called groups and 12 horizontal rows called periods. In every group, a gradation of physical and chemical properties of elements was observed. The table provided gaps for undiscovered elements. The table helped predict the properties of 3 elements. These elements were named Eka, boron, Eka, aluminium, and Eka, silicon. When these elements were discovered, they were named scandium, gallium, and germanium. The properties of these elements were very close to those predicted by Mendeleev. Like other attempts at classification of elements, Mendeleev's periodic table also had some merits and demerits. Let's take a look at the merits first. The table helped in the correction of atomic mass for many elements. It predicted the existence of some elements that had not been discovered at the time that the table was created. Because of its merits, the periodic table is widely accepted as a system of classification. However, it did not achieve complete success because of some demerits. The table had some inaccuracies. For example, the table reversed the atomic weights of 2 pairs of elements. A. Iodine, with atomic weight 127, came after tellurium, with atomic weight 128. B. Nickel, with atomic weight is 58.68, came after cobalt, whose atomic weight is 58.94. Alkali metals such as sodium and potassium, and coinage metals such as copper, silver, and gold were placed in the same group, even though their properties are significantly different. Lanthanides and actinides were not given proper place in the periodic table. Isotopes did not find a place in the periodic table. The table did not clearly indicate the position of hydrogen.
Now let us understand the periodic table. Period 1 consists of hydrogen and helium. Period 2 consists of lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So total 8. Period 3 consists of sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. 8 elements are there. Then period 4 consists of potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, and krypton. So total, how many electrons are there? How many elements are there? 18. Now, number of valence electrons will not remain same. They will change. That means either they will increase or decrease. So we'll study periodic properties in detail. Periodic properties occur because of same outermost or valence electron configuration. Now lithium electronic configuration is 2,1, sodium is 281, potassium is 2881. So outermost electronic configuration keeps on repeating, and so as the periodic properties.
H. J. Moseley, an English physicist, built further on the periodic table to resolve the problems encountered in using it. He discovered that atomic number is a better basis for classifying elements than atomic weight. On the basis of his work, he developed the modern periodic law. The modern periodic law states the physical and chemical properties of all elements are periodic functions of their atomic numbers. The modern periodic law has become the universally accepted form of classification of elements, as it does not suffer from the demerits of Mendeleev's periodic table. The periodic table, developed by Mendeleev, was intended to illustrate the arrangement of elements using atomic weight as the basis of classification. However, this arrangement showed some anomalies, like elements with higher atomic weights were placed before elements with lower atomic weights. For example, the atomic weight of cobalt is 58.94 and that of nickel is 58.68. However, the Mendeleev's periodic table places cobalt before nickel. Such anomalies were resolved when the modern periodic law designated atomic number as the criterion for classification. In this lesson, you will learn in detail about the modern periodic law and the modern periodic table. At the end of this lesson, you will be able to explain how the modern periodic table is arranged, explain the reasons for classifying elements on the basis of atomic number, describe the features of the modern periodic table, and identify the trends observed in the modern periodic table. The modern periodic law was developed by Moseley, an English physicist. This law states that the atomic number is a better basis for classification of elements than atomic weight. This law formed the basis for the modern periodic table. Atomic number is the number of protons in an atom. It is also equal to the number of electrons in the atom, since an atom is electrically neutral. For example, the sodium atom contains 11 protons and 11 electrons. Therefore, the atomic number of sodium is 11. Similarly, the atomic number of magnesium is 12. Since the atomic number of magnesium is higher than that of sodium, magnesium is placed after sodium in the modern periodic table. Electronic configuration of an atom is the arrangement of electrons around its nucleus, which affects the properties of the atom. Bohr, a Danish physicist, tried to explain the behavior of atoms through his atomic structure theory. According to his theory, electrons are not located randomly around an atom's nucleus, but occur in definite electron shells. Electrons in the outermost shell of an atom are the ones involved in chemical reactions. These electrons are called valence electrons. The shells in an atom can be named alphabetically as shell K, L, M, N, and so on. Each shell in an atom has a limited capacity for electrons. The K shell can accommodate 2 electrons. The L shell can accommodate 8 electrons. The M shell can accommodate 18 electrons. The N shell can accommodate 32 electrons. As the lower shells are filled up, the additional electrons are placed in more distant shells.
is 1 by 1. Atomic size. What is atomic size? What do you understand by the term atomic size? The distance from the center of nucleus to the outermost shell is called as atomic size, or it is also called as atomic radius. Now, how we determine the size? Like the size of circle is determined by the radius. So in the same way, size of atom can be determined by the atomic radius. So atomic size is determined by atomic radius. Unit is angstrom. Now let us understand what is ionization potential. Ionization potential is also denoted by I. Ionization potential means the amount of energy required to remove an electron from the outermost shell of an isolated gaseous atom. You can see here M is the atom, it becomes a ion, and the energy is called as IP, or ionization potential. Now let us understand electron affinity. The amount of energy released when an atom in gaseous state accepts an electron to form an anion. Generally, non-metal accepts electron and becomes anion. Here we have taken the example of chlorine. Electronic configuration of chlorine is 287. So it requires one electron to complete its octet. So it accepts one electron and becomes chloride. So this is all about electronic affinity. We have seen periodic properties including atomic radius or atomic size, ionization potential, and electron affinity.
Electron affinity. Electron affinity is the amount of energy released when one or more electron is added to the outermost shell of an isolated gaseous atom. Electron affinity depends on atomic radius, nuclear charge, and electronic configuration of the element. It is expressed in electron volts.